Welcome to The Explainer. Okay, today we are diving deep, literally, to untangle a massive engineering puzzle. We're going to explore exactly how complex subsea fields route millions of dollars of production every single day without completely breaking the budget in the process. It is an absolute masterclass in structural optimization, and let me tell you, the stakes down there are incredibly high.
Okay, let's dive into this. Picture this scenario for a second. You've got 6 different wells sitting on the seabed, all producing highly valuable fluid. But you only have one pipeline to carry it all the way up to the host facility miles away. How does that actually happen? I mean, getting fluid from multiple distinct wellheads into a single, perfectly managed stream doesn't happen by accident. It requires a brilliantly purposeful physical setup.
Which brings us right to Section 1, the commingling problem and the economics of seabed architecture. Now, what's really interesting about this is the sheer scale of the cost involved. If you're building a subsea field, you are immediately up against some absolute mountains of capital expenditure. Deep water engineering is punishingly expensive. Think about it. If all 6 of those wells each ran a dedicated flow line directly back to the host instead of sharing one, what happens? Well, exactly what you'd guess. You're paying for 6 times the pipe material, 6 times the installation vessel time, and you end up with this wildly inflated seabed footprint and a blown budget. On the flip side, commingled flow lines share that pipeline infrastructure. It optimizes your cost and creates a beautifully streamlined export route.
So how do we actually achieve that commingling? That brings us to Section 2, the subsea manifold, basically the highway interchange of the deep.
So, the crucial point is that the subsea manifold is your active problem solver down there. It's a massive structural frame packed with complex piping and valve arrangements, specifically designed to commingle, distribute, and control the production from multiple wells into those shared flow lines. Imagine a really busy highway interchange. You've got several on-ramps, which are our individual wells, and they are all merging safely into one main highway heading straight to the host.
You see, the manifold isn't just a heavy piece of plumbing, it's a highly strategic cost optimization tool. By commingling that production, it drastically reduces your total flowline count, saving enormous capex right from the earliest planning stages. But it's also smart. Crucially, it includes isolation valves for every single well. This means you can easily shut down or run maintenance on one individual well without disrupting the flow of the entire system. It's a real game changer for field layouts. But routing all this fluid together creates a pretty terrifying hidden danger. Welcome to Section 3, the thermal expansion threat and the intense physics of high pressure and high temperature. Here is the underlying mechanism. As hot fluid from deep within the earth rushes through and heats that high-pressure steel pipe, the pipe naturally wants to expand and grow longer. It's just basic physics, right? But because that pipe is resting heavily on the seabed, buried or otherwise restricted from moving freely, all of that pent-up thermal energy violently converts into axial compressive stress, pushing intensely outward against both ends of the flow line. And we are talking about hundreds of tons of force here. Just let that number sink in for a second. Hundreds of tons of sheer mechanical pressure pushing against the very ends of your flow line. If you do not have a way to securely hold that pipe in place, it is going to buckle, shift, and literally tear your field apart. So, how do we tame that absolute beast of a physical threat? That leads us to Section 4, anchoring the flow line and what I like to call the suspension bridge anchor. Enter the PLT, or pipeline end termination. It's this incredibly heavily founded subsea structure that steps in to manage all those structural forces at the far end of a flow line, acting as your fixed anchor point. Think of it exactly like the massive, solid concrete anchor holding down the main cable of a suspension bridge. It has to be built massively, frequently secured with the exact same suction pile foundation technology we covered back in episode 1.4, just so it can hold that enormous tension and compression without moving a single millimeter. And this brilliantly illustrates the contrast between these two giants of the seabed. They play distinct, yet totally complementary roles. The manifold's primary function is flow commingling, acting like that highway interchange to optimize your capex. Meanwhile, the PLET is all about structural anchoring. Its main benefit is managing that terrifying thermal expansion, acting like your suspension bridge anchor. You absolutely need both heavy pieces of steel to make the field work. Okay, but what happens if you get the math wrong? If the foundation capacity of that PLET is undersized, it simply cannot resist the actual thermal expansion force. Remember, this isn't about static weight, it's entirely about thermal force. If the PLET shifts out of position under that intense load, the connected jumpers get pulled entirely out of tolerance, instantly creating critical leak paths. A single shift can literally mean an environmental disaster and millions of dollars lost.
Let's move to and see how this builds. Section 5, bridging the gap and connecting our fixed points. Because here's the harsh reality of subsea engineering. Things never, ever land exactly perfectly as designed on the seabed. Ocean currents, installation tolerances, and vessel precision mean there is always a gap between the as-designed drawings on a computer and the as-built reality down on the ocean floor. You're dropping heavy machinery through thousands of feet of moving water. Real-world imperfections are a guarantee, so we need highly flexible final-stage connections. That critical final connection is the subsea jumper. It is a short, connecting pipe section that physically bridges the gap and accommodates all that positional and thermal misalignment between two fixed subsea structures. It's the missing link. Whether it's connecting the tree to the manifold or the manifold over to the PLET, the jumper's entire job is to absorb that inevitable misalignment. Now, engineers generally have two choices here, and it's a direct engineering trade-off. First, you have flexible jumpers. These are incredibly forgiving of measurement variations. They can absorb large misalignments, kind of like wearing an adjustable belt. But they definitely have limits when it comes to extreme pressures and temperatures. On the other hand, you have rigid jumpers. These are tailored for exact gaps and are fully capable of handling intense high-pressure, high-temperature service. But the catch? They require incredibly precise post-installation metrology to get the fit exactly right. Pulling off a rigid jumper installation is an incredible sequencing challenge. First, you have to successfully install your fixed seabed structures. Second, you send down an ROV to conduct a centimeter-accurate metrology survey of the actual gap on the seabed. Third, you fabricate the jumper on the surface to match that exact measured gap. And finally, you lower it down and connect it on the very first attempt. You literally cannot build a rigid jumper until the structures are successfully surveyed sitting in the mud. And because of all that, jumper selection is actually one of the very few major subsea component decisions that happens incredibly late in a project. It is decided only after the structures are actually installed and surveyed. The final connective tissue of your multi-million-dollar field is heavily, sometimes entirely, dependent on actual as-built conditions. It's fascinating. So I want to leave you with this to think about. If a single mathematical error allows hundreds of tons of thermal force to shift that massive PLE anchor even just a few inches, what happens to those perfectly measured, inflexible, rigid jumpers connected to it? The stakes are astronomical, the tolerances are microscopic, and that right there is what makes subsea architecture so absolutely fascinating. Thanks so much for joining this explainer, and we will see you next time.